So when we talk about how these things are built, now in the modern world, we've got, computer and numerical controlled machinery for rolling shells into particular shapes and drilling holes in the particular patterns and tube sheets and all this kind of stuff. So, the CNC control is very, very big. And inside of a fabrication shop, they've got all of the pressure welders and the boiler makers, and they're all certified and they're all up to date, and they've got nice, quiet, still conditions inside of the plant. So if you can imagine, I'm going to draw a weld joint here for you. Oops, that's a really bad weld joint. Let me do that again. There's my V groove, and then here's the metal. And so let's say I'm welding gas metal arc welding. And so here's my electrode, and I got an arc going on in there, and I'm depositing weld metal, and I got the shielding gas that comes from my MIG machine, or maybe I'm welding TIG. Even if I'm doing shielded metal arc welding, I do get some shielding gas from the decomposition of the electrode coating. And if it's breezy, like it is outside today, so here's my cloud with puffy cheeks, and it's got pursed lips, and my cloud is blowing wind, and it's going to blow away that shielding gas, and when it blows away the shielding gas, I get porosity. So what I'm trying to say is we've got excellent control of placement of holes and dimensions of drums and all this kind of stuff, because we've got all the machinery right there in the shop. We've got nice conditions for the welders to do their work. It's not windy. It's not minus 30 outside. It's not plus 40 outside. These welders are working in controlled conditions in the shop. And then what I'm going to do is I'm going to do post-weld heat treatment, and I'm going to take that whole boiler and I'm going to stick it into a furnace and give it some stress relief. So the point of what I'm saying is, with a package boiler, we can really assure high quality. And because we produce a lot of these small package boilers, it's like assembly line work. It's like making a Chevy car, right? You make one after another after another. And after a while, you get pretty good at it, right? And so a Cleaver Brooks Model 5 that we've got on the 4th floor of the Synovus building is just like any other Model 5 everywhere else in the world. So they develop routines and procedures, and they can refine the product, and they can select proper burners and controls and all this kind of stuff. So this is one of the advantages of a packaged boiler, is really the high quality and the high quality build. But one of the drawbacks is they're limited to fairly small sizes. So this boiler here, I think I said last time, was a B&W type FM. And so one of the things is, if I wanted, say, a 5,000 kilowatt boiler, it would have particular dimensions. It would have a particular, maybe a particular height, and it would have a particular width, and it would have a particular length. And with a package boiler, they're completely built in the factory. So now they got to go from the factory to your home or to your plant. So how do you get it from the factory to your plant? Well, I'll tell you, we're going to put it on a train. We're going to put it on a flatbed truck. And the train or the truck has got to go through a tunnel. And the tunnel has a particular height restriction. And driving down the highway or on a railway track, there'd be a width restriction. So these package boilers are limited in height and width. So what if I like this B&W Type FM boiler, but I need a larger one? I need one that's 8,000 kilowatts. Well, how do I make it fit on the train tracks? What I do is I just make it longer. Instead of having, say, I don't know, let's say instead of having 200 tubes in the boiler bank, maybe because it's longer, I'm going to have, say, an extra 100 tubes in the boiler bank. So this is how we increase the capacity of the boiler, by increasing the heat transfer surface area of the boiler. And the only dimension that we can play with, really, with a package boiler is its length. So we find that in larger capacities, they get longer, and they max out, really, let's say around 2,000 boiler horsepower, which is the same as 20,000 kilowatts. That's really as big as these suckers get. And if you need something bigger, then what you're looking at is a shop assembled boiler. So, okay, you think, well, how big is, say, a 20,000 kilowatt boiler? Well, I think it would be a little bit bigger than the B&W Type FMs that you see in the SAIT powerhouse. Okay, the SAIT powerhouse, those are package boilers, but they're getting toward the upper end, the upper size of things. Package boilers also include all of the Synovus building boilers. They're all package boilers. So you can see, like, boiler number 4 has got a superheater. So we can actually have economizers and superheaters on package boilers too. Everything is sized to fit. Everything works together. And a good quality control. They're hydrostatically tested and signed off in the factory. So actually what they get is they get a National Board inspector to go to the factory. And then National Board Certified Inspector is going to inspect the welds and the fit up and all this kind of stuff. We'll probably put some what we call hold points during the production of that and say, I want to inspect the steam drum once it's all fit up. And then I want to inspect the mud drum. And then after I've done that, then I want to be there for the hydrostatic test. So those would be like 3 hold points on a document, and the document is called a traveler, and the traveler goes between the manufacturer and the inspection agency, so that they know, oh yes, I'm going to need you in my plant on next Tuesday to do a hydrostatic test on these 10 boilers that we've just finished. So that's what's going on in the factory with package boilers. Whereas a shop assembled boiler, like we said, is much larger. Now, we might have with the shop assembled boilers, most of the components hydrostatically tested and signed off in the factory, as well as post-weld heat treatment. But we got some components here, like maybe we've got our superheater bank or the burner or whatever. We're going to limit the field welding. So when they're doing the final assembly, it could just be like a bolt-up situation where you've got these, a class 600 flange between the steam outlet and the superheater bank. So they, put a gasket in there and they bolt it up so that there's no field welding. So without any field welding, we don't have to do any field stress relief. That's not to say there isn't any field welding with regard to one of these shop assembled boilers, but it would be minimal compared to that done with a field directed boiler. If you want to learn more about shop assembled boilers, I would suggest you go to Cleaver Brooks online. And Cleaver Brooks has a line of very large shop assembled boilers. They in fact use that terminology, shop assembled boilers. And the brand, I guess, is called Nebraska. So you can look up Nebraska boilers and just see their brochure and see how a shop assembled boiler differs from a what the heck package boiler. And as for the field erected, well, when we get into chapter 3, I'll show you about field erecting boilers. We're going to kind of go through a boiler. A friend of mine was a boiler maker and an instructor for boiler makers in Manitoba for a long time. And so he gave me a whole bunch of pictures of the erection of a field erected boiler in Ontario. It's a power boiler that is being built for a pulp and paper facility, and so he gave me freedom to use those pictures. So you'll see when we get into the third chapter, the boiler erection stuff. It's very, very interesting stuff. And that is really where we left off. I just wanted to add those few extra little points. But one thing about this field erected boiler is that it's built in the shop. So like, let's say the steam drum is built in the shop, mud drum built in the shop, maybe an entire water wall is built in the shop, maybe an entire superheater bank is built in the shop, and things that can be post-weld heat treated in the shop are done. So there'd be a big shop, and they'd have a big furnace, and then they'd put the steam drum in there, and they'd put the mud drum in there, and they'd do the post-weld heat treatment. And but that doesn't mean there's no field welding. So here we can see maybe this is an external downcomer. I'm not too sure. I think maybe that's a downcomer. And maybe this drum has got tube stubs all the way along. And so what they have to do is a butt weld. They'll do a butt weld there, and they might do, say, 100 butt welds along the length of the drum. And then they might do another 100 butt welds along there. And of course, they're doing this in minus 25 weather, and they're doing it in plus 35 weather, and they're doing it in the rain, and they're doing it in the snow and the sunshine and all this kind of stuff. So really, really talented boiler makers are working on this stuff, and really, really talented welders. And so ultimately, once this thing is all put together, the hydrostatic test, which is part of the final sign-off, is done in the field. And that would be signed off by a national board certified inspector, who then would affix the nameplate and the serial number and the ASME S stamp on the boiler in the field. So there's our field erected boiler. Now, oops, wrong way. Now the next thing that's covered in Objective 1 is this boiler rating business. And boiler rating is really about steam output capacity. And in a sense, we kind of looked at this already. We looked at ASME Code Section 1, and we looked at non-mandatory Appendix A44. And A44 had some stuff in it. They said there was one column that said square feet of heat transfer surface, and then the SI equivalent in square meters was beside it. And on this table they had, I think they had stoker fired, and then they had gas and oil fired, and then they had, I don't know, pulverized coal or something like that. And then they had boiler surface, and then they had water wall surface. Okay, and there was this table, and it would tell you how many pounds per hour or kilograms per hour of steam could be generated from a certain amount of heat transfer surface area. And I think that A44 has a title something like Method of Determining the Steaming Capacity of the Boiler Based upon Square Foot or Square Meters of Heat Transfer Surface Area. Basically, this is what a boiler manufacturer does when they want to determine the boiler's rating, when they want to determine what's its steam capacity. So it's a non-mandatory appendix, which means that they don't have to follow those rules, but it's a guideline for the manufacturer. So if the boiler manufacturer wants to make a boiler that can produce 600,000 kilograms of steam per hour, then they can even sort of work backwards and say, well, how much water wall surface area do we need? And how much boiler surface area do we need? And if we know that, then we kind of get an idea how big the boiler is going to be physically. And then, they can say that this is the rated steam capacity of the boiler. Now, this is important because in terms of boiler capacity, well, first of all, the jurisdiction wants to know. So if you're installing a boiler in Saskatchewan or Alberta or Ontario, New Brunswick, the jurisdiction has laws that says, okay, this is a first-class plant or second or third or fourth, and they want to know that it is staffed correctly. So that's one of the reasons, the authority with jurisdiction or having jurisdiction wants to know. They need to know. It's the law. And then think too about a designer. So let's say I'm an engineer and I'm designing a plant, and I know that the processes within the plant, this process uses 10,000 kilograms of steam per hour. This other one uses 5,000 kilograms of steam per hour, and on and on and on. So I can determine, the steam load, and I can put in some sort of a factor in terms of overcapacity. Do I want the boilers to have sufficient capacity for future expansion of the plant, and on and on and on. So not only is boiler capacity important to us power engineers and the authority with jurisdiction who are mandating the staffing, but also for the engineers who are designing. They need to know how much steam a boiler can produce. So that then is this term that we call rating. So when we talk about the boiler rating, we can talk about an energy transfer rate, or we can talk about steam production. And again, that would be a rate, so steam production per unit time. And really, if you take a look at that carefully, it's the same thing, isn't it? Because the steam's leaving the boiler with energy. So if I've got a small boiler, we might use the term boiler horsepower. Now, boiler horsepower it's an old term. It's not SI. Okay, so a lot of jurisdictions in Canada, because Canada is a metric country, a lot of jurisdictions have moved away from the boiler horsepower, and they just use the kilowatt instead. However, in the USA, boiler horsepower is very, very commonly used, and we see it in North American manufacturers of boilers and pressure vessels, whether it's in Canada or the USA. So Cleaver Brooks, Saskatoon, and other manufacturers often rate their boilers in boiler horsepower. So we're going to have to look a little bit into boiler horsepower and see exactly what that is. And by the way, this abbreviation, I looked really hard a number of years ago to find out what is the abbreviation for boiler horsepower. It's different from brake horsepower. BHP would be brake horsepower, which would be mechanical, but boiler horsepower is B small o HP, and that comes from the United Kingdom. So kind of interesting. So I'm going to use that BOHP stands for boiler horsepower. So boiler horsepower is an energy transfer rate, and it's 33,475 BTUs, that's British thermal units per hour. So you can see that it is an energy rate. And because it is an energy rate, well, we know what a kilowatt is. It's a kilojoule per second. So we can easily convert between boiler horsepower and kilowatt. And what we find, it's about a 10-to-1 ratio. So what that means is that 1 boiler horsepower is about equal to 10 kilowatts. Not exactly. This would be a soft conversion, but it's the conversion. It's simple to use. And because it's simple to use, it's simple even enough for lawmakers. So if you go to, different provinces and look in their regulations, you'll see that they often use that soft conversion. They say 1 boiler horsepower is 10 kilowatts, or 10 kilowatts is 1 boiler horsepower. And that when you buy a boiler and it's stamped on the side of it, this is its boiler horsepower, then the jurisdiction can deal with it easily. They go, oh, well, times 10, that gives me the kilowatts. Now, there are other units that are in use, and one of them, boy, baffles me. I don't know what a therm hour is. I think at one time I did research it. That used to be used in Ontario. I don't know if they still do use the therm hour, but in the Ontario legislation, they use therm hours. So again, that's actually an energy rate. Does anybody here know what a therm hour is? Raise your hands if you know what a therm hour is. Good. I'm glad. So these systems here are basically informative for us when we are trying to also determine the classification of a plant. And in Alberta, 10,000 kilowatts, or 1,000 boiler horsepower, is, if we exceed 1,000 kilowatts or 10,000 kilowatts or 1,000 boiler horsepower, what we have is a first class plant. So you should have the regulations. You should be familiar with them because they are going to govern how you conduct your work going forward as a power engineer. And then I think that if Alberta is like Manitoba, and I think it is, 5,000 kilowatts or 500 boiler horsepower, if we exceed that, but we're up to and including 1,000 boiler horsepower, what we have is a second class plant. But what if we've got something that's like 250,000 kilowatts? It's like, oh my God, that's a first class plant 10 times over. There reaches a sort of a practical limit where the kilowatt rating or the boiler horsepower rating isn't very informative from a jurisdictional standpoint. There's little, there's bigger, and then there's bigger, and then there's biggest, and then there's oh my God, right? And once you get to the oh my God section, everything's a first class plant. So at that time, they start to deal with a unit that should be on my list here, typically for generating stations, megawatts electric. So how do you classify a boiler? What you do is you look at the electric generator that is driven by the turbine that is supplied by the boiler. And typically what we have in generating stations are units. And a unit is a boiler, a turbine, condenser, boiler feed pump, back to the boiler. So this is a unit. We don't have multiple boilers on a single header. We don't even have an interconnection between the steam headers. I worked in a plant that had 2 units. Units were self-contained. There was no communication of water or steam between one or the other unit. So what we can do is take a look at the generator or the alternator at the back end of it, and we can say, oh, that alternator puts out so many megawatts of electric power. And that's what we rate the boiler as, in megawatts electric. So as you go through literature, maybe you're doing a capstone project and maybe it has to do with power generation, you'll see that a lot of boilers are not rated in boiler horsepower or kilowatts or pounds per hour of steam or anything like that. They'll be rated in megawatts electric. Then there are other very, very useful terms, ways of rating boilers, pounds per hour and kilograms per hour. And see that for, say, a system designer, knowing how many kilograms per hour of steam a boiler can generate is very, very important. So this then is sort of my little introduction into boiler ratings. Let's look a little bit more at the boiler horsepower. It's ancient. I would say it is over 120 years old. And, you know, we do use it for package boilers, say under 2,000 boiler horsepower or so, but it's just not a common term for anything larger than that. So now, because there is this sort of 10-to-1 ratio of boiler horsepower to kilowatts, I am also going to strike out the boiler horsepower, and I'm also going to add here the kilowatt, because that's becoming more common. Now, how do we determine the kilowatt rating of a boiler or the boiler horsepower rating of a boiler? Well, we got a couple of different ways. The first one is the rated boiler horsepower. And I want to zoom in on the word rated here, as opposed to the developed boiler horsepower. So anyway, Chrysler made this monster engine called the 426 Hemi, and it was in some of the, you know, the biggest muscle cars of the late 60s, Barracudas and Dodge Chargers and stuff like that. And they rated that engine at 425 mechanical horsepower. That was its rated horsepower, was 425. Now, back in the day, some people, you know, took these engines and actually tested them on an engine dynamometer, and they found that they were actually producing around 500 horsepower. So even though the engine was rated at 425, it really put out like 500 horsepower. So this engine became kind of legendary, you know, with muscle car enthusiasts, everybody, all 426 Hemi. Same with a boiler. We have got a rating, and then we got its developed boiler horsepower. So what we're going to do is look at rated horsepower and developed horsepower, and then look at this term percent rating. What we're going to see is that the rated boiler horsepower is based upon this rule: 10 square feet of heat transfer surface area equals 1 boiler horsepower. And if I do the stock conversion into SI units, which is very, very common in the regulations across Canada, say 1 square meter, because 10 square feet is kind of close to a square meter, is equal to 10 kilowatts. And so this is the kind of soft conversion that's done by the legislative authorities across Canada. This is called rated boiler horsepower. Why do you need to know this? Because that's what ABSA uses. Now, developed boiler horsepower is used by some other jurisdictions. So, for example, I was a boiler inspector in the province of Manitoba, and one of the things that I had to do was to determine the classifications of plants. And Manitoba had 3 ways of determining the classification of plant. And what it would say is, figure it out, do 3 different calculations, and pick the biggest number. That was Manitoba's approach. So the first approach was to take the heat transfer surface area and use that, for every 10 square feet of heat transfer surface area, that's 1 boiler horsepower. That's one way that Manitoba said you can determine the boiler horsepower of a plant. Then the second way was to do developed boiler horsepower, and there were 2 methods for determining developed horsepower. And the funny thing was those 2 methods gave you the exact same answer. And then what we had to do, this is what the law said, the inspector shall select the larger of the 2 numbers. So if this 426 Hemi was a boiler, I would, say, oh, it's 425 horsepower would be its rated horsepower, and then the developed horsepower would be like 500 boiler horsepower. Say, oh, that's a 500 horsepower boiler. And then somebody could complain and say, no, it's not that big, it's not that big. And I go, oh, the law says to use the largest number. And in this case, the largest number would be 500. So developed boiler horsepower used in many jurisdictions across Canada. But Alberta likes to stick with this one here, rated boiler horsepower. So we're going to get more into that. And then there's the concept of percent rating. So if we have a boiler that develops 500, but its rating is 425, then we do a little bit of mathematics. And let me just see here, 500 divided, this should be really simple. I could do this in my head. 118%. So if we had a boiler that was rated for 425, but it actually produced 500, and let's say kilowatts in this case, then we would say that this boiler operates at 118% of its rating. Makes sense? It puts out more than the manufacturer has rated it at based upon its square footage of heat transfer surface area. So the rated boiler horsepower, and again, we can also be talking about the rated kilowatt. So this is based upon square feet or square meters of heating surface. And here's the history. This is why it is so darn old. I don't know when James Watt was building his first steam engine. I'm going to say late 1700s, early 1800s. I don't know, but old. And, James Watt's steam engine was an improvement on other designs, and it's essentially the kind of reciprocating steam engine that is in use in some places today. And so he did some experiments, and he said, in order for my steam engine to produce 1 brake horsepower, okay, that's a kind of mechanical horsepower that's determined by actually putting a brake on the engine. And in order for that to produce 1 brake horsepower, I had to put in 33,475 British thermal units of energy per hour. And so then James Watt thought, oh, well, how much is 33,475 BTUs per hour? Well, what he did was he looked at the latent heat of evaporation of steam. And he said that, 1 pound, see, I'm switching to imperial units here, but you should recognize the terminology. It's the same stuff you studied in SI units, but now we're in imperial units, which is what James Watt would have used. So to get 33,475 BTUs, knowing that the latent heat of evaporation of water at atmospheric pressure, 14.7 psi, is 970 BTUs per pound, he figured out that he needed 34.5 pounds, or the energy in 34.5 pounds of dry and saturated steam that was developed from feed water at 212 degrees Fahrenheit. Okay, so what James Watt said was, okay, my boiler doesn't really operate at atmospheric pressure, and I don't have feed water at 212 Fahrenheit, but let's use that as our baseline. Let's take the latent heat of evaporation as our baseline and say, I need 34.5 pounds of steam. So then the boilers of his day were so old. Think about HRTs if you studied that stuff, or what were some of those other boilers, Haycock boilers and wagon boilers. You know, these were very old shell type boilers that were very, very inefficient. And so what he found out was, from his experiments, it took 10 square feet of heat transfer surface area to put out 34.5 pounds of steam. And that 34.5 pounds of steam would have 33,475 BTUs in it, so his engine could put out 1 mechanical horsepower. So that is how this nonsense began way, way back when. And we still use it today in the province of Alberta. So here's just sort of a nice little picture, and we'll just forget about that 42,000 BTUs. We're going to put in feed water at 212 degrees Fahrenheit, and we are going to produce dry and saturated steam at 212 degrees Fahrenheit, and of course we know that that's 100 degrees Celsius. And we've got a boiler here that's got 10 square feet of heat transfer surface, or in a soft SI conversion, let's call it 1 square meter. And so that 1 square meter, that 10 square feet is going to put out 34.5 pounds of steam. And then, there's, not 33,475. I actually should say that, but 33,500 is good enough. Goes into a steam engine, and he gets a mechanical horsepower out. Not a boiler horsepower, but a mechanical horsepower. This is where this came from. Now, non-mandatory Appendix A44 says that currently 10 square feet of heat transfer surface area produces anywhere from, I'm thinking about, I don't have the numbers handy, but I think up to like around 160 pounds of steam. Oh no, I think that's 1 square foot. 1 square foot of heat transfer surface, 160 pounds of steam. Well, that's a hell of a lot more than boilers were putting out in James Watt's day. So my question is, why hasn't the concept of boiler horsepower kept up with what ASME says about how much steam 1 square foot produces? I don't know the answer to that. I think I do, but I think it's a political answer, so I'm not going to go there. So anyway, there's a slide that shows you all the various hard conversions. If you wonder what a BTU is very, very similar in size to a kilojoule. And 10 square feet is actually 0.929 square meters. So this is how the soft conversion really works well. You know, like it's close, right? And let's make it easy um, for jurisdictions and lawyers to deal with. So if we do a hard conversion, we can say 0.929 square meters produces 35,307 kilojoules, which produces 9.3 mechanical kilowatts. But instead, let's do it a soft way and say we got a square meter and 36,000 kilojoules, and we got 10 kilowatts. And then this is what we have in our ABSA. You'll notice that this number 36,000 kilojoules is mentioned in the ABSA documents as well as in your Pan Global. The 10 kilowatts equaling 1 boiler horsepower is also, I believe, in ABSA. And that's the only way that they do it. On the left, I've got an old style rated boiler. And so let's say that we're talking about boilers in our lab. And let's say that we've got a boiler that has, let's say, 3,650 square feet of heat transfer surface. And let's say I got another boiler somewhere that has got, 273 square meters of heat transfer surface. The boiler on the left here, what's its boiler horsepower rating?
365.
Here we go. Thanks for that. And the boiler on the right, what's its kilowatt rating?
2730.
Right. 2730 kilowatts. Now let's do soft conversion. Let's take this one here, and we're going to express it in terms of kilowatts using a soft conversion. And the soft conversion is 10 kilowatts is equal to 1 boiler horsepower.
3650 kilowatt hours.
Got to get rid of the hours, just 3650 kilowatts. Yeah, yeah. Okay, so there, that's about as complicated as it gets. Now, one other thing that's mentioned in your Pan Global text is when it comes to electric boilers, and this is pretty common. Electric boilers, basically, they are rated according to the kilowatt input. So if you're operating a large electric boiler and it's 3,000 kilowatt electric boiler, then that's what its rating is, 3,000 kilowatts. I'm not going to do that. What I do want to mention is that this equivalent evaporation is related to developed boiler horsepower. So when we talk about developed boiler horsepower, we're actually looking at how much the boiler actually evaporates. And you, I think, have done equivalent evaporation in Therm, either last term or you got it happening this term. You would have done equivalent evaporation, and you would have done factor of evaporation, and I think you would have done there's another one there. Anyway, it's also in your Pan Global, in your academic supplement, so if you want to look it over again. But ultimately, developed boiler horsepower is based upon equivalent evaporation of a boiler. So, if you don't believe all of that crap I just laid on you, this is from Babcock and Wilcox from a book called The Stirling Water Tube Boiler that they produced in 1912. 1912, so that's what, 109 years ago. 110-year-old book, okay? And this is just to show you how old that ABSA method, the 10 square feet or 10 square feet is 1 boiler horsepower. That nonsense. Okay. So they use the term rated horsepower, and they base that on the boiler heating surface. So I'm not making this up. Notice this boiler here has 3288 square feet of heat transfer surface area. This is somewhere in Los Angeles. And they are rating that boiler at 329 boiler horsepower. There's our 10 to 1. And here's one in Chicago for a steel company that has 3,612 square feet of heating surface area, and they're rating it at 361. So that's its rated power. And then they're applying equivalent evaporation rule and blah, blah, blah. And notice that they use feed water at 212 Fahrenheit, producing dry and saturated steam at 212 degrees Fahrenheit. So this is the actual equivalent evaporation. And they can take the equivalent evaporation divided by 34.5, which gives them developed boiler horsepower, which I'm not going to go into. So here's the developed bit. And so for this first boiler, this Los Angeles boiler, it develops about 340 horsepower. Oh, it's only rated 329, but it develops 340. So it is operating at 103% rating. And if you take a look at the Chicago boiler here, and they do the equivalent evaporation on it, and blah, blah, blah. And what they find is the developed horsepower of that one is 642 boiler horsepower. And if I go 642 over what its rating was, 361, that gives me the percent rating. And this boiler is operating at 178% of what it's rated at. Okay, so this stuff here, this is ABSA. And then this here is the real world. The effect is, for us as power engineers, is a smaller boiler in a different jurisdiction might be a first-class plant. But in Alberta, that same boiler might be a second-class plant, or maybe even a third-class plant. So what it really means is that in Alberta, ABSA has fairly lenient regulations because they use this rule. Okay, you need to have a whopping big boiler to get your 1,000 boiler horsepower, or your 10,000 kilowatts if you're dealing in SI units. So I'm not going to go over the summer thing. I could beat that horse dead, but you can look it up in the slides and the PowerPoint and the lecture notes and stuff like that. So we're all the way now onto objective 2, and these ones go a lot faster. And this is all about water circulation and the factors that influence circulation. So I'm going to warn you a little bit. The third class overlaps the fourth a lot, especially in some of these content areas. And in that regard, what's the point? The courses were originally designed back in the 1940s and 50s by SAIT, and they were designed for correspondence. And if somebody is a correspondent third-class student, they might be rusty with their fourth-class knowledge. So there was a deliberate insertion of repeated content in the third. And then they repeat some content again in the second, and then in the first. And as far as I'm concerned, that overlap should have been removed. As a matter of fact, it has been removed over the last few years, but it's a long and tedious process, and this is what PanGlobal and IPEC and SOPEAC are working on, is getting rid of some of the overlap in terms of the curriculum. So I don't want to bore you with fourth class materials and just repeat them. What I am going to do is cover third class, and we're going to get into some interesting terminology that we find in the second class. And I want to present the information in a way that's going to challenge you a little bit and maybe get you interested, because I don't want to give you the same crap over and over again. I think that that's just an injustice. So please bear with me and don't complain too much, and you're going to find that I'm going to take you, okay, so let's say that the second class is here and the third class is here. What I'm going to do is take you in terms of your knowledge of the content is going to be somewhere, in between those two. And if you know this stuff well, when ABSA tests you down here, you should be a hot shot at the third class content. Okay, so I'm going to take you a little bit beyond, but don't worry, we are going to cover what you need for the third class. So we're going to start and we're going to look at what goes on in a boiler like an engineer does. And so we've got a particular amount of heat that goes into that tube. And then we've got a particular mass flow through that tube. And at some point, we're going to start generating steam, and we're going to get stuff coming out of the tube, which might be two-phase. But in this instant, we're going to just deal with single phase. And we got stuff that comes in with a particular mass flow rate at T1, and it leaves at T2. Bear in mind that this boiler tube has got a maximum temperature that it can handle, okay? So we know that the Q out is going to be equal to MC delta T. So what we need is, in our boiler, when we start talking about circulation, we need to know that Q in must be at all times equal to Q out. If that is not the case, then what happens is T2 will increase. Well, actually, no. That would still be the same thing as increasing Q out. If it is not the case, then what we end up with is an increase in the tube wall temperature. Temperature of the tube is going to increase possibly beyond its ability to withstand the elevated pressure at such an elevated temperature. So let me put this in simple ways. We need to keep the tube cool. And so when firing rate increases, if we want to maintain the same T2, then mass flow must also increase. And as firing rate decreases, similarly, we should see a drop in the mass flow rate through the tube. So let's keep that stuff in mind as we start looking at circulation patterns in boilers. So here are two diagrams here. And for the one that's on the left, I'm going to put a mudroom here and a riser. Put MD for mudroom. And then this is going to be the downcomer, right? Downcomer. And riser. So on the left, we see the boiler that you're all familiar with, right? Every boiler that you've operated in the Synovus building, and quite possibly outside of the Synovus building, has been one of these things. And this is the boiler that has internal recirculation. So we can call that a recirculating boiler. Whereas the one on the right, we have to think of something like this. I got a boiler feed pump, and I'm pumping water into the tube, and what comes out the other end is steam, and there you go. It's that simple. This boiler here on the right has no internal recirculation, and so we call that a once through steam generator, no TSG. So let's take a look at what's going on with the recirculation boiler here. We can have recirculating boilers that use natural circulation, or we can have forced circulation. So let's look at, first of all, the natural circulation, because this one here involves a little bit more theory. Notice that in the riser, I've got a whole bunch of steam bubbles here, and we've got a particular density. So if I measure sort of this height here, is the height of the riser, and I take a look at the column, and I take a look at the density, rho, sub r for the riser. And then I look at the downcomer here, and there's no steam bubbles in the downcomer. So the downcomer, same height. So the height of the downcomer equals the height of the riser. And now we have a particular density, a particular rho in the downcomer. And now I'm going to put a little pressure gauge at the bottom. So there's the pressure at the base of the downcomer, P sub D. And then I got a pressure gauge here at the bottom of the riser, P sub R. And we know that pressure is equal to rho G H. Well, given that the height of the downcomer is the same as the height of the riser, and given that the force of gravity should theoretically be the same on both the riser and downcomer, we can see that pressure is going to be dependent really on the density of the fluid in the downcomer versus the riser. So that difference in pressure between PD and PR, so PD minus PR, is basically the static pressure. And we're going to call this the natural pumping head. There was a reason you took pumps last term, right? And if the boiler is at a particular firing rate, given its design, it should always have so many bubbles here and no bubbles there. This difference in density between the downcomer and the riser is provides us the natural pumping head in that particular boiler that feeds water from the mud drum into the risers. Okay, and again, we need to have a particular mass flow that varies with the Q input. So the mass flow has to vary with the heating input, and we see that due to the increase or decrease in number of bubbles in the risers, we in fact see a changing density in the riser with firing rate. So let's say we've got sort of a low firing rate right now. So you can see all those bubbles. Well, if my heat input goes up, then I see more bubbles and larger bubbles. And those more and larger bubbles reduce this pressure here at the base of the riser. And so then the differential pressure increases, and so then the natural pumping head also increases so that mass flow increases. Okay? And I can draw that on a little chart. I can say firing rate on the x-axis increasing, and mass flow rate here. And as firing rate increases, mass flow increases. Firing rate increases, mass flow increases. And we're going to revisit this a little bit later on another slide. We're going to look at it in a little bit more detail. But I hope that that makes sense. We fire it harder, we make more bubbles. This becomes less dense compared to the dense in the downcomer, and so we get greater circulation through that boiler. Let's say that I've got 1 kilogram of two-phase stuff going up the riser. 1 kilogram is going into the steam drum. And let's say that of that 1 kilogram, I've got 0.8 kilograms of steam leaves the drum. What that means is that I've got 0.2 kilograms going back to the mud drum. And then we can add a flow rate to that as well, right? We can say per second or per hour, whatever units we want to use for time. So this then is what we call the recirculation rate. And recirculation rates vary from, say, 4 to 20% in a boiler, in a natural, well, in a water tube boiler. In this case here, well, you can figure out the percentage, but I think actually this is 20%, isn't it? So 20% of the water in this case is actually recirculating. And you might go, well, look, you're losing 0.8 kilograms. For every kilogram that comes up, we're losing 0.8. We're going to run out of water because we're only recirculating 0.2. Ah, yeah, but we got feed water going in. And the feed water is going to be 0.8 kilograms. So you got 0.8 kilograms comes in as feed water, and notice that it matches the steam output, and 0.2 recirculates. So that's how we get this term recirculating boiler, and recirculation rate then is how much water recirculates in the boiler. So now let's take a look at the one-screw steam generator here. And we're going to take a look at some of the things that are going on. And I'm going to introduce some terminology that's not in the third, but you'll definitely encounter it in the second class. And it's helpful at this point to know some of this terminology. So here we've got one phase. And really what we have is subcooled liquid. And you're going to go, cooled, it's hot. Yeah, it's hot, right? But it's not boiling yet. So it's considered to be subcooled. And then we start to see some bubbles forming. And what is going on here is what we call bubbly flow, or bubbly boiling, because you got bubbles. I know that sounds so cheesy, but this is where I'm going to introduce the neat technical term. It's what we call nucleate boiling, and that's a term that you need to know. Nucleate boiling. And you wonder, well, why nucleate? Because we consider each one of these to be a little nucleus, okay? Nuclei. So there, we got nuclear boiling. This is what we're used to seeing in the kettle and the pot on the stove and stuff like that, right? And then you increase the firing rate and the bubbles get bigger and bigger and bigger. Okay, and so in this particular once through steam generator, it reaches a point where we no longer have nucleate boiling. And this point here, we are going to say there is a departure. Departure from nucleate boiling. And I know you probably think that this terminology is a lot of BS. This is the terminology that we use at the second class level. Departure from nucleate boiling, we abbreviate with the TLA. You do know what a TLA is, right? TLA is a three-letter acronym. So the T that we use is DNB, departure from nucleate boiling. It means we're not nucleate boiling anymore, we're doing something else. So this type of boiling that's going on here is what we call a couple of different terms. We can call it film boiling, or we can call it annular boiling. Depends who you're reading or where you're reading it. And when you think about it, what we have is water is along each side of the tube, and sort of like one gigantic steam cavity in the middle. And so if I was to take a look at a cross section of that tube, there's my tube, and I would see, water in this annular ring of water keeping the tube cool. Okay, so that's film boiling or annular boiling. And then above here, what we have is, well, there's some different terms. I'm just going to say here we got steam. And so there's some drying going on here, and maybe there's superheating going on. Okay, so that's going on in a once through steam generator. We're going from single phase water coming in to steam coming out. So I'm going to erase the slide one more time. Any questions about what I just mentioned? Okay, then we are going to now look at these boiling patterns and see what happens in a recirculating type of water tube boiler. So we got a particular heat input, and we got nucleate boiling. And if I was to take a sample of the two-phase mixture there, I could say that I've got a certain amount of steam and I got a certain amount of water. And we can talk about the dryness fraction, right? And so we can say that, say, it's 20% wet. Meaning that, or no, pardon, 20% dry or 80% wet. Okay? And if we look at the 20% dry, there's a term that we can use to describe the water at the top of the riser when it enters into the steam drum, and that term is another one you need to know. It's called top dryness. And so in this example I've given, we would say we've got 20% top dryness. Now, that is, maybe a reasonable design dryness. So with a particular maximum heat input that we don't want to exceed, normally on this particular boiler design that I'm talking about, we've got 20% top dryness. and that's adequate to keep the top of the tubes cool. But if we overfire, okay, we know that the circulation should increase, the mass flow should increase for the tube, and it should prevent excessive top dryness. Because if we have excessive top dryness, then we're going to burn out tubes. What we're going to have is, with excessive overfiring and excessive top dryness, our riser is going to look kind of like this picture over here, where we will have a departure from nucleate boiling and film boiling, and then perhaps we can go 100% dry where the tube is entering into the steam drum, which would be really, really bad, because that would indicate that we're going to overheat the tubes and potentially make them fail. But we know that the mass flow is supposed to increase with firing rate. So going back to our little diagram, we know that Q increases, and because of the difference in density, the mass flow should also increase. And what we find is it's not exactly proportional. And eventually reaches a point where the mass flow isn't going to increase. So recall that we had pressure at the base of the downcomer, and we had pressure at the base of the riser. Gives us the delta P, which is our natural pumping head. However, well, this natural pumping head is really like the static head. Given our maximum firing rate, design firing rate, we should get a maximum delta P, which is really static. But we know from pumping studies that there are dynamic head losses. And what do we have in a boiler? We got a bunch of pipes. We call them tubes. We got some bends. In piping world, we call them elbows. You know, we got particular pipe schedules. And we got pipe sizes, and some pipes are small internal diameter, and some pipes are large internal diameter. So we got all these different diameters. And then we've also got different lengths of pipes. So we got a boiler that's really, really tall, or we got a boiler that's really, really short. And then we got one boiler here where they do really good water treatment, and the tubes are gunmetal clean inside. And then, you know, some other sloppy engineers, and they got all the scale buildup in their tubes that's causing a restriction in the tubes. So as flow increases, mass flow increases, so do dynamic pumping head losses. And you know that from the pumping lab last term. So dynamic head losses increase with mass flow. So yeah, we would like to say, oh yeah, you fire it harder, you make more bubbles, and it becomes less dense, and you get more pumping head. But only to a maximum. After which, the dynamic head losses interfere with an increase in the flow of water through the tubes. Does that make sense? So let's now look at the scenario where we are going to exceed the maximum design firing rate of the boiler. We are going to overfire. We're going to put in way too much Q. And we've made lots of bubbles, and instead of having one phase down here, we've actually got some nucleate boiling going down there. And then maybe right about there, we're going to get a departure from nucleate boiling, and we're going to start entering a film boiling phase. And then we're going to get up here where we're actually I think the term is called mist boiling. I'm not too sure, but no, we just got, you know, a little bit of entrained moisture, and then over here, maybe it's dry and saturated. At which point we would have 100% top dryness, and we would get tube overheat and failure. Okay. So, in other words, this once through steam generator tube, well, that's what the riser is going to look like. Okay. We don't, OTSGs are designed for this. Recirculating boilers are not. So let's make this just a little bit practical. You got a boiler and your burner is a piece of crap. It's 20 years old, it's not very efficient, and you've suffered 5 years of flame outs and flame failures, and it just seems to have a mind of its own, and you're tired of this thing, and you go, that crappy burner, time for a new burner. And you're the chief engineer, and you're lucky enough to look through burner catalogs and say, okay, I want this burner. I want a low NOx burner. I want it to be dual fuel. I want it to be oil. I want it to be gas. Now you got to say to yourself, wait a minute. How big of a burner can I put on my boiler? And if you're a bit of a meathead, you'll go, oh, well, that was a 50,000 kilowatt boiler. And if I put a bigger burner on it, I can get 80,000 kilowatts out of it. Well, maybe you can, but maybe if you're at 80,000 kilowatts, you're trending downward already, and you're going to overfire it, and you're going to have excessive top dryness, and you're going to burn out the tops of your tubes because you had departure from nucleate boiling and things just got too hot. So what you're going to do then is you're going to check the nameplate information on your boiler. You're maybe going to contact the boiler manufacturer. You'll ask them, what is the maximum firing rate for that particular boiler design? And can you recommend any compatible burners? Because we don't like the one that we got on it right now. We've got this Riello burner, and we want to put on a whatever different brand. Okay, so this is where it becomes practical in terms of sizing the burner to the boiler. It's a very important design exercise. Now, one other thing I want to point out on here is I'm going to overfire this boiler. Too much heat. And I'm going to have a departure from nucleate boiling over here, and then I'm going to have film boiling or annular boiling over here. Now, if Q is so high that it causes 100% dryness, that amount of Q that causes this is called the critical, another term you need to know, critical heat flux, or CHF. So, flux is a Greek word, it means flow. And the critical heat flux or critical heat flow is the amount of heat input into a tube at which film boiling ceases and dryness, drying out begins. Okay, so right here at this point, we have obviously reached the critical heat flux of that particular tube. Oh boy, you guys are getting your money's worth today. Oh, they don't pay me enough to teach this stuff. So this slide here shows you, and I am looking away, just so you know, shows forced circulation and recirculating boilers. And so this is how they are categorized or pardon me, forced circulation and natural circulation boilers. This is how it is categorized in your Pan Global. And so if they ask you to regurgitate something like this on your ABS exam, so these are the two categories: forced circulation and natural circulation. For the forced circulation boilers, they can be recirculating designs, which we haven't looked at yet, or they can be once-through steam generators. Each one of those types can be forced circulation. As a matter of fact, all OTSGs are forced circulation. The natural circulation, well, we just looked at that in detail. That's based upon the natural pumping head. And so we've already looked at some of these things. So the natural circulation boiler does have internal recirculation. And so water comes in from the economizer and goes through the downcomer. And then we got risers, brings two-phase into the steam drum, and then a certain percentage of it recirculates, and a certain percentage of it goes out with the steam. So what are the factors in natural circulation? The factors are boiler operating pressure. So we said that the pressure at the base of the riser and the pressure at the base of the downcomer are dependent upon rho of the downcomer and rho of the riser. And what we find, well, we know that density, rho, is equal to 1 over the V G, or rho is 1 over VF. It depends what phase we're talking about, whether it's in the gaseous phase or the fluid phase. But it's still density, right? And what we find then is as boiler operating pressures increase, the difference between the specific volume of a gas and a specific volume of a fluid decrease until we get to a critical pressure and temperature. So you recall from the steam tables, and I can draw, I can plot out the steam tables, and we reach this point here where VF and VG are the same. Okay, we call that the critical pressure. And what we find is if VG equals VF, then rho sub downcomer is going to be equal to rho sub riser. And if rho sub downcomer equals rho sub riser, then the P at the base of the downcomer is the same as the P is at the riser, and we get no circulation. So boiler operating pressure is a very important design factor in terms of whether a boiler is going to be natural circulation or whether it needs a pump assist. And we find that natural circulation is used up to, say, a maximum of around, 12 to 14 megapascals, somewhere in that range. It's a very crude kind of rule. But so all natural circulation boilers can be operating somewhere below that. Now, as for feed water temperature, if my steam drum is at, say, 320 degrees Celsius, that's your saturation temperature, then we want the fluid going in to be somewhat cooler than that. So let's say 20 to 40 degrees below the saturation temperature. And that way, adding cool, dense liquid, that cool, dense liquid will help to promote the natural circulation by making the downcomer density a little bit greater. And of course, the height of the boiler is a factor because we know that pressure is equal to rho GH. And so obviously, if we've got a very high boiler, then we should see a greater difference between the pressure at the base of the downcomer versus the pressure at the base of the riser. But there is a practical height limit. I mean, we don't want to make a boiler that's 30 stories tall, you know. And then, of course, we know about the dynamic pumping losses. So, you know, the longer the tubes, the greater the dynamic head losses and trying to overcome it. So there's a practical maximum to the height of a boiler in terms of how it increases or how its flow rate increases with regard to height. Okay, greater length of pipe, greater length of tube, greater restriction. So it's not an equal type of gain for proportional gain in mass flow compared to height. Now we know about firing rate. We know what that does to circulation. So firing rate goes up, so mass flow should go up, but it reaches a maximum. And then there's the whole tube cleanliness issue, which is really a question about cross-sectional area of the pipe, as well as roughness of the pipe. So if we get lots of scale on the inside, it reduces the cross-sectional flow area and also increases the internal roughness, so which will also affect the circulation. But we can also say that fireside cleanliness affects Q input. So if we get a lot of ash buildup, then it will also affect circulation rate. So I'm going to end with these words here. Let's say that these are all design factors. Boiler operating pressure, feed water temperature, height of the boiler. This is all a matter of design. This is stuff that we can control from an operating standpoint. That's all I got for you today, folks.